What's up, everybody? Welcome to part 4 of this tutorial series on using the KITTI Odometry dataset with OpenCV and Python. In the first video, I went through the fundamentals of camera projection matrices and the math that's going to help us do photogrammetric computer vision that we're going to use to do this visual odometry. In the second video, we made a class object to handle the dataset to, make it easy to work with. In the third video, we talked about how to get depth information from our stereo pairs of images. And then so now we're going to be able to use that depth information to do visual odometry. And the way that this works is that we're going to take an image from one frame and then estimate the depths of all the pixels in that image. And then we're going to find features in that image that are distinct, like say the corner of a building or something, like that in the image. And then we're going to find features in the next image, and then we're going to match them. So the corner of the building in one frame, then the car moves, and then we find the corner of that same building in the next frame, and then we see how it's moved through the image, and then that's going to allow us to determine or estimate how the camera has moved between those two frames. So to detect these features, we're going to be using SIFT, which is a kind of a classic method of doing this. It's very robust. It's quite effective. For a long time, it was patented so that you could only really use it for academic purposes. But now the patent has expired, so you can use it, and it's very effective. Except the only problem is that it's kind of slow, so it doesn't really work in real time. It takes probably at least 300 milliseconds, whereas our camera frame rate is 10 frames per second, which is 100 milliseconds. So this is more for theoretical demonstration of the process. SIFT works pretty well, and I think that anybody who's getting into computer vision and photogrammetry and that kind of thing, you need to know about SIFT. And so that's what we're going to be using. If this is sort of a launching off point, so as you go forward from here, you can use faster things, and we'll go into orb a bit. It hasn't worked quite as well for me, but anyhow. So yeah, we'll go ahead and get started. I do want to say one thing first, is that for those who have been following along in the series so far, sorry there was a little bit of a long gap between this video and the last one. I got kind of bogged down with research that I need to be doing. So, and I was also trying to, brush up on the theory that I was going to put into this video. But today I've got some time, so we're just going to push through. I'm not going to be, try and make this too much of a perfectionism thing, because what I'm going to do is I have good resources for other people that explain the theoretics or the theory behind what we're doing here far more in depth. And then those videos by themselves are an hour long. So, this video series is more about putting these concepts into practice and then demonstrating that. And then from there, you can go back and dig into the real fundamentals of what's happening to your heart's desire. Really, you can go in and you can do all the research and the underlying processes that we're doing here. I'm going to explain, the best that I can what we're doing, but it would just be way too long of a video to explain everything about how SIFT works and then show how we're going to use that on the KITTI dataset. So I'm going to refer you to some really good sources, particularly this one YouTube channel with Cyrill Stachniss. I think it's how you say his name. I'm not sure. He's the German head professor at the University of Bonn in Germany. He has a YouTube channel that I'm going to show you and link in the description, and his explanations or lectures that he's put on YouTube are extremely good. And so to dig into the details, I'm going to refer you to that. Here, we're going to put it into practice on the KITTI dataset. So let's get started here. So another quick point that I want to make is in the last video I put out, which I called part 3.5, because it wasn't quite, it was sort of a side quest on doing some fun stuff with projecting the LiDAR point cloud onto the image plane and then making videos out of that, and just sort of playing with this data. And so for the people who watched that video, I did make a bit of a mistake right at the end, which is that I did scale the disparity, because we saw that trippy thing that ended up getting made because I skipped this step at first. But then I didn't do it for the point cloud. So I don't think that this line was in there. And so I'm going to run this cell just so you can see how it should have looked. And then maybe this will inspire some of you to go back and watch part 3.5 in case you want to. Oop, no, well, let's go to full screen mode so you can see what's going on here. And so, yeah, you can see that the point cloud down here is much darker now, and that's because the lighter colors represent more depth. So the further things are away, the brighter they are. And that's the way it should have looked before. And this is actually like harder to see than what we had, but the problem is that because I had not scaled the these between 0 and 1 and then multiplied back by 255, is that when you do the cv2.m show, it like wraps the values when they go past the values that it expects. So it goes from like, from darkest to lightest and then back to darkest to lightest. And so it creates sort of this like segmented ramp structure of like, from dark to bright to dark to bright to dark to bright. And so I kind of messed that up. So I just wanted to cover that real quick. And if you're curious about all the stuff that we did here to make those little videos happen, watch the last video. It was part 3.5. And then there's one more quick point I want to make, because I think some people might have caught that there was something interesting that happened back here, where I have this Boolean flag RGB equals false, and then down here the color conversion, which we're not even using in this, I just added it as an extra feature, is blue, green, red to gray, even though this is an RGB flag. And so this isn't necessarily a mistake. It's because when you read an image with, so let me think if I can figure out easily where the images are here. I think I can probably do that. So let's like pull a test image out real quick. Image equals, what is it going to be? I'm getting a little sidetracked here, but it's okay, because see, we're reading these images as grayscale. Well, they are grayscale images. We downloaded the black and white data set. So let me just breeze through this real quick. The difference is that when you read an image with plt.mshow and you put in some file path here, the result is going to be a NumPy array tensor that has 3 channels, and those channels are going to be RGB. Now, if you do this with, or I'm sorry, it's supposed to be mread. Yeah, this will return, if you read a color picture, it's going to be a m height by m width by 3 tensor, and those 3 channels are going to be in the order RGB. And if you do this with cv2.mread, this is going to return the same shape, except that the channels are going to be in blue, green, red order. So you have to keep that in mind when you're working with reading images, is that if you use matplotlib to read them, they're going to, if they're color, they're going to be RGB. And if you use CV2 to read them, they're going to be BGR. So don't get tripped up. Like I said, we're not even using that functionality in this tutorial series because our images are grayscale from the get-go, so we're not converting them to, sorry, I'm scrolling all around here. I'm looking for where we were, whatever. Yeah, here it is. The RGB equals false. It's because when I made this function the first time, when they were colored pictures, I was reading them with CV2. So I was converting them to grayscale by using BGR to gray because that was the color format that they were in after I read them. And the flag was just called RGB because that's what I called it. But so that's definitely important to know. That's why I wanted to cover it. Uh, PLT reads it as RGB, CV2 reads it as blue, green, red. So be aware of that in the future when you're working with colored pictures, because if you mix and match the two, you might get tripped up. So I'm not going to cover all the stuff we've done because that would be redundant. This is all the stuff that I've done in the last few videos, starting from the second video here. These are all the packages that we're using, trying not to use anything too fancy. Obviously, we're using OpenCV, and I have pandas in here because I think that I was reading the CSV files with that, and because pandas makes that really easy. So that's what's going on. So let's get started. We are at the point now where we have our depths. So now that we have a depth estimation mapping for every pixel in an image, then we want to find features in the image using SIFT, and then those features that we find in the first image that we match with corresponding features in the next image. We're going to, in the first image, use our depth information for every pixel. Wherever the feature that we're locating that we're matching into the next picture is in pixel coordinates, we're going to take the depth that we have estimated for that pixel, and then we're going to reconstruct the 3D position of that feature in the 3D coordinate world of the first camera, well, the first frame's camera. So where the camera is in the first frame, or rather the frame that we're starting from, because this is going to be done in a sequential fashion. So for every frame that we're doing this, we're going to be estimating depth for this frame. We're going to be finding features in this frame, and then we're going to take the next frame and match features between these two time frames, and then use the 3D reconstruction of the points in the earlier frame to estimate camera change in position with a actual metric foundation, because it is possible to reconstruct 3D motion without knowing depth, but without knowing depth, and you do that, you don't actually have your scale involved. So you can say, you can recreate the trajectory between all of your sequential positions of the camera, and it'll have the same shape as it would doing it the way that we're going to do, except you would have no idea how far the camera points are apart. All you would have would be like a relative unitless reconstruction of a 3D motion through space, but you wouldn't have any idea of the actual distance. Or so basically, if you, it would just be some factor of the actual distance that you traveled. So anyways, yeah, this is going to be a recursive thing. So, and so the function that we're going to use to figure out the 3D motion between one frame and the next frame is going to be the perspective endpoint algorithm, and we're going to do it with ransack to handle the outliers. And it's really effective. CV2 makes it really easy because it has this function built into itself, so we don't have to, you know, code all of this by hand. I do recommend that you go and you read about how perspective endpoint works, and especially ransack, because ransack comes up all the time in computer vision. It's a super powerful way of handling outliers, and I'll explain it a bit more in a second. But so basically the idea is that if you have a camera that's taken a picture, and then you find features in that picture, and you recreate them in a 3D world that corresponds to the coordinate frame of that camera's position in the first frame that you're thinking about, then these points in the 3D world, when the camera moves and it takes another picture, and those same features, we're going to match them, appear in the new image, then you can figure out where the camera is in that 3D world now based off of the locations of those features in the new image. So, and then you can do that just by trying to find a translation and rotation which satisfies where you would expect these 3D points, where they're now landing on a 2D image plane. And so you don't actually need to know their 3D locations in the second image. You just need to establish their 3D locations in the first image, then find them in the 2D second image, and then you solve for a translation and rotation that puts them into that where they're now found in the new image. So we have our depth ability. I've already run all these cells. And so we're going to go ahead and first we need to make a function that extracts features from a picture. So we're going to say def extract features, take in an image. We're going to take in an argument to tell us what kind of detector we want to use. We're going to use SIFT, and then we're going to take in a mask if we want one. And as I explained before, the facility of using a mask is that when we do these depth estimations, you can see that there's a rectangle over here where we have just useless information, where we don't know the depth of things over here, because this is where everything to the right of here is where the stereo images actually overlapped. And since we're using stereo to estimate depth, anything over here where the right camera didn't have information, we don't have depth information. And so running a feature extractor in this area and finding features here would not be helpful, and it would just add extra computation that we don't need, because if we find features over here, we're not going to be able to use them because we don't have a good depth estimate for where that feature is in the 3D world. So by using a mask, we add computational efficiency to keep, from doing useless math on every frame. And so we're making this function. This is going to be a pretty simple function, because we're just going to say if detector is SIFT, then we're going to create a detector object from cv2.sift create. I want to mention that depending on the version of CV2 that you have, this might be a little different, so just look up for yourself, because they have this X features 2D, yeah. And then I think it's under, yeah. So let me add some space here. This, when you have the newer versions of CV2, this is how you write it, because now that SIFT is no longer patented because the patent expired, they took it out of X features 2D, which was like they buried it in there to make it harder to get to, I guess. But it was never illegal to use it for academic purposes. It's just that if you were going to deploy it in some commercial application that you were charging money for, then you would have needed to pay some fee to the creator of SIFT. But that is no longer the case because it's old. But it really goes to show how effective it is, because people still use it all the time, and it's it's been whatever it is, 20 or 25 years is how long it takes a patent to expire. So it's really stood the test of time. So we're going to be using it here for demonstration. And then I'm also going to add functionality for orb, because orb was created as an alternative to SIFT, and it's faster, and a lot of people get it to work really well. I have not gotten it to work for myself. Maybe somebody can fill me in on the deets on why it isn't working well for me. But to get that, all we got to do is say cv2.orb create. And so this will make our detector object. And so something to note about the difference between SIFT and orb is that SIFT creates, let's talk a little bit about feature descriptors, because I talked about how we're going to find distinct features in these images, like the corner of a building, or the tip of a fire hydrant, or a window on the corner of a window of a building. These are the kind of features that are distinct in computer vision, that between one image and another image will be easy to track, because they don't look like other things. And it's sort of the way your vision works. And so I have here, this is the OpenCV, the little blog post of theirs, like the introduction to SIFT. And there's some useful graphics here, because they're going to be finding features using difference of Gaussian in this SIFT object that we're using. And so basically they take the image and then they apply varying levels of Gaussian blur to the image by running a Gaussian kernel over it to blur it. And then they take the differences of those blurred results, and these are then the differences of each of those different layers of varying amounts of blur. And then so they find features by finding things that stand out in those differences between those Gaussian blurs. And then what they do is they then scale the image by an octave, and they do the same process again. And so they find if there are features that appear distinct at the new scale that were also distinct at a larger scale, and then I think they do this a few times. This is what makes it scale invariant features. So that's the whole name of SIFT, scale invariant feature transform, is because they're trying to find features that are distinct even if they're further away. So let's say your car is moving very fast toward a building, then in the first image you find a feature which is the corner of that building is going to be pretty far away, and then by the time the camera takes another picture, you're a lot closer to the building. Now the corner of that building is much larger in the image. It's going to be scaled much differently between those two images. So this is why SIFT is great, because the feature is still distinct. It has the same characteristics despite the fact that it is now much larger. And so it makes it robust. And then it goes a step further in that it does an orientation assignment so that it becomes orientation invariant, or rotation invariant rather. So this is much more effective than the sort of old school corner detections and stuff like that, when they were finding like corners in images, because they weren't scale and rotation invariant, and SIFT is. So this is exactly why we're going to be using SIFT. So now is where I want to point out Cyrill Stachniss, his YouTube video. I'm butchering his name. I feel bad about that, but anyways, he has an entire series on photogrammetric computer vision, and this is just one of the videos. This one in particular, you can see he's using the same exact graphic we were just looking at, which I guess comes from this paper from Lowe, who I'm going to discuss in a second. But his videos are really good. They're very long. He goes through everything and discusses things at great length about the mechanics of how these things work. So that's a good reason why I don't want to get too redundant here, because the material is available here. And here's part one of key points, where he discusses more of the edge and corner detection. And then in part two, he goes more into SIFT and the more advanced algorithms. So that's sort of my little summary of what's going on here, so you know. And so yeah, I think that that's enough to move forward with. Okay, so the thing about SIFT is that the descriptors that it generates, so let's go back over here because not only does it, the features are detected, so the key points is what those are called, are the points in the image that are distinct. Then once you know a distinct point, you want to find a way to describe it. So you get a feature descriptor. And SIFT has a very particular way that this is done, which was what was patented, is that it creates a histogram of gradient orientations in a part of the image around the key point of interest. And so if you want to learn more about how that works, watch his video here. He discusses it great. And so those feature descriptors are these, I think they're 128 numbers long. So it's like a vector that's 128 numbers long, or whatever, however long it is. I'm pretty sure it's 128, it says right here. And each of those numbers describes a part of this big histogram on these gradients in different orientations. So it's, yeah, I don't want to get too detailed here because I'm just going to take up too much time. And so the thing is, it boils down to a one-dimensional vector that's 128 numbers long. And so when you detect more features in the second image, and you want to figure out which of those features between the first and the second image are the same thing, then you want to find the features which have the most similar descriptors. And since these descriptors are vectors, we can use different types of distances between them to describe their similarity. And so in this case, we'll be using L2 distance, which is essentially Euclidean distance. So just the way that you find the distance between 2 points in space by using Euclidean distance, where you add all of the squares together and then take the square root of all the squared values. That's L2, that's Euclidean distance. So that's what we'll be using. So that works with continuous values, which these are. When you're using orb, the orb descriptors are binary. So they are also a vector of numbers, but that vector of numbers only has zeros and ones in it. And so when you want to find the distance or the similarity between vectors that contain binary values like that, you use norm Hamming, or rather Hamming distance, which is, you know, I can pull it up, but you know, you check it for yourself. There's just a whole different kind of math. We'll just pull it up right now. Hamming distance is just a way of finding the distance between two vectors that only have binary values. And yeah, I won't go too into this. The underlying concept here is that the descriptors are vectors, and to find features similarity, we want to find the features that have the least amount of distance between their descriptors. And that will tell us which features are most likely to be the same. So the corner of the building that I was talking about earlier, it's going to have a particular descriptor attached to it. And then in the second image, that same corner of that same building may be in a totally different part of the image. It may be a different size. And so when we need to figure out mathematically whether or not this feature is indeed the same feature from the last image, we want to find the new feature that has the smallest distance in between its descriptor vector and the descriptor vector of whatever feature from the last image. So I hope that that was not too long-winded. So now we go ahead and use whatever detector object we have created, and we use the method detect and compute. Come on, autocomplete, you got it. I think my computer is working pretty hard today. I'm doing a big download. It's because I haven't initiated the object officially. So, okay. No matter whether it's a SIFT or an orb detector object, it's going to have this same method, detect and compute. And this means that we detect the key points using the difference of Gaussians, and then we compute the descriptors either using SIFT or orb, which will create those vectors that we're going to use to match them with. And so we'll get a list of each, and then we'll return those. So return the key points and return the descriptors. And there we go. So not a lot of complicated stuff there. Now we're going to make a function to match our features once we get them. So we're going to say def match features. We're going to say list of the descriptors from the first image, list of descriptors from the second image, a matching type, which I'm going to set to BF. I'll explain that. It means brute force. Detector equals SIFT. In this case, is going to be our default. Sort equals true, and k equals 2. I don't know if I want to sort them or not. Can't remember. I'll figure that out in a second. Sorry to throw too many curveballs. There's a lot of code that I've made like kind of a while ago now. I'm going through. I'm like, is that a good idea? I'm pretty sure it was working, so won't mess with it. So anyways, we're matching the features now, and there's two ways to go about matching, which is, well, there's more than two, but we'll cover two here. There's brute force, which is what I described before, which is where we're going to use the math to calculate the distance between the two vectors. And then there's another way that people do it, which is called a KD tree, which is basically where they partition space recursively to find the nearest neighbors rather than using calculated distance, which has advantages in especially, I think, high dimensional space. But it's funny because when I ran this and timed the difference, I actually found the brute force to be faster, which wasn't really what I expected. But I think it's important for me to cover that there is an option here, because when you go off and do this more on your own, you don't want to be in the dark about the fact that brute force is not the only way to do this. And yeah, because really the whole point in matching features, as I said, is we're trying to figure out the closest descriptors between two features. And that'll tell us which ones match. So like I said, if you're using SIFT, you're going to be using a different type of matching math than if you're using orb. So this is why we're going to set up a if statement here, to where if we're using SIFT, then we're going to use BF matcher create, and we're going to do cv2 dot norm L2, which is Euclidean distance I just described, and set cross check to false. I'm not going to go into that because it's just not going to come up, but I'm putting it in there so that you can see that that's a thing. I don't know. I don't feel comfortable enough talking about what that does. Specifically, we're not going to be using it because we're going to be using, instead of just returning one match per feature in the first image, we're going to be returning two nearest neighbors. And the reason that we're going to return two nearest neighbors is because we're going to use the difference in distance between the first match and the second match of any given feature in order to tell us how good of a feature it really is. Because if you have some feature and then it is assigned a match in the second image, and they have some distance between their descriptors, and then you find the second closest match to the feature in the first image that has some distance between their descriptors, and the difference between the distances that it has between its closest match and its second closest match is not very large, then that means that that feature has been, like, matched between two different features in the second image sort of relatively equally, which means that it isn't really that good of a feature. Because if you, between your first and second closest match, don't have a pretty big gap in similarity, then that means it's kind of a fudgy match. It doesn't stand out as like, wow, these two are definitely matched. You're talking about a sort of a weak feature, and we're going to leave those out by using that as a comparison, which is a technique that was introduced by Lowe, and we'll go into that more in just a second. So it's called the ratio test. And so basically you take the distances of the first and second match, you just find the ratio between them, and if that ratio is not below a certain amount, then you just ignore it and you move on to better features. So then if we're using orb, we're going to want our matcher to be another brute force matcher, but instead of using L2 distance, we're going to use Hamming distance. I'm going to use Hamming 2. Cross check equals false. Cool. So now, depending on the detector that we used to extract features, we will be using the appropriate distance metric to match them in our match features function. And so we're going to say elif matching equals flan, which is the other method that we're going to have available to us. And like I said, I won't be able to describe all these things down to the science or the theory. So but I'm showing you these things so that you have a place to start in your own research to dig in deeper. And also because we're able here to put these things into practice so that you can see what we get done, and then later you can fill in your knowledge gaps. So it's sort of a bit of a redundant step, but it's descriptive, is that we're telling CV2 that we want it to use algorithm number 1, which corresponds to the KD tree algorithm I was telling you about, which is one of the options within a flan matcher. And you should look up KD tree on your own. Can't cover it here. It's, like I said, it's a recursive partitioning of space to find nearest neighbors, rather than using a brute force calculated distance metric, which may be more computationally intensive in certain situations. So something to definitely keep in your toolbox for later. And if you go into the notebook that is in the repository for this whole tutorial series, the big notebook where all of this is written out, I've run the final result using SIFT, using orb, using brute force, using flan to time the differences, to see what the difference in accuracy, like overall error in the end is, and I left all that in the cells of the notebook. So if you want to dig in deeper, you really should have this repository cloned and go into that notebook where I wrote it all out and tested everything, because that's going to be very informative. So I don't know why I put spaces here. I like spaces on my arguments. So yeah, these are just some sort of out of the box parameter arguments to pass into these functions that I'm pretty sure I just took them from some example to get it to work, and so wasn't a whole lot of reasoning other than using the parameters that were recommended to me. I'm sure that these values can be tweaked and then monitored for changes in performance, but as you'll see, this is going to be a time-consuming process. So by all means, on your own, tweak these values, see if it improves things, and then if it does, let me know, because I'm curious. But I'm already bad enough about blabbing a lot in these videos. It makes them all very long, but I hope it's it's informative. It's supposed to be sort of a low-level explanation of these things, really get into the nitty-gritty, and then also demonstrate everything in practice. So this is where if sort, we're going to say matches equals sorted matches, and we'll say key equals lambda x, where we're using, so the matches will be objects which have a what was the word, variable called distance attached to them, an instance variable called distance. And since we're using this KNN match, which is, it's kind of funny. Okay, I missed that up here. Yeah, we don't need, this is supposed to be outside of here, because either way, no matter whether your matcher is a flan-based matcher or your matcher is a brute force matcher, we're going to use KNN match for the exact reason that I described a moment ago, which is that we want to have two matches per feature, so that we can determine whether that feature is really good by seeing if the second match that it comes up with is significantly further in similarity than the first match it gets, and he'll tell us whether or not that match is good. And I've set k equals to 2 up here. Okay, and so here's the sorting function if we want that to happen. I might set that to false here in a minute, because I'm just not sure. But so, okay, this is everything here. This is how we're going to match our features. I think I've described how it all works. So cool. Now we can extract and match features between two images. So let's see sort of what this looks like to make sure everything is working. First of all, we'll go ahead and make a function to visualize our matches. We're going to take in first image, key points for that image, and an image, second image, and key points for the second image, and then the matches between the two images. And we're going to say image matches equals cv2.draw matches. That super convenient function for doing exactly this. And we're just going to pass in the exact things that we have, which is a little less convenient because we have to say, I can't remember what the none is for. Yeah, the output image, because we're actually returning an image. Yeah, CV2 a lot of the times, especially when you're using it with C++, you don't really return values like this. You sort of pass a matrix or an image in to it, and then it applies changes to that matrix as the function runs. But in Python, we're sort of used to returning objects from a function and then reassigning them to a variable here. So that's why this is here. The more you use CV2, the more you'll see what I'm saying. And then we need flags equals 2, and trying to remember what that is. It doesn't say here. It don't have written down why flags equals 2 for draw matches, but I don't want to be omitting things here, so let's say cv2.draw matches and see if we can figure out what flags equals 2 is. Matches. Okay. Sorry, I'm kind of going on a tangent here. I just hate writing things in there and not telling you what they mean. There's definitely a reason. I think that this is it. It just means that key points without a match might not be drawn. I'm not sure. Just keep it equal to 2, and maybe I'll put something in the description about what that means. I know where to find the information because I know where I learned to do this, but I don't have it on hand. Okay, so here we are. We're going to make a figure that's, you know, this size is going to be handy for this application. We're setting DPI equals 100, and then we're going to say imshow image matches. And so now let's check our pipeline so far. We have extract features where we're going to have an image detector and mask. Earlier we made a mask and called it mask, I believe. Or did we? Yeah, so I already have a variable called mask that looks like this. And basically, yeah, if you've been following along with the videos, then we covered this. And so I'm not going to do it again. You know, go back if you need to. It's going to be in the 3rd video. Yeah, the last, yeah, part 3. And so this is the mask that we're going to be using. It's called mask, so you're not surprised where that's coming from. And so we need to extract the features in both images, which is going to return key points and descriptors for both of those images. And so here's what we're going to do. We're going to say image left equals handler dot first image left and image right. Just like shorten up these variable names so that we're not, you know, writing a book. Right. Then we need to get a depth map between our images because that's what we're going to use. Actually, we don't need this right now because we're just visualizing. So let's go ahead and say key points 0. I'd like to start with 0 here, and descriptor 0 equals oh man, I'm using that, huh? Oh, okay. Sorry, I'm getting a little confused here. I'm going out of order. Extract features image left. And we're, of course, using SIFT, and we'll pass in our mask. And then, descriptor 1. Okay, so instead of using image right, that's not, image right would give us the depth. What we want is image plus 1, which is the next image on the left camera, because that's the whole point of what we're doing, is using sequential images. So the key points and descriptors that we're finding now are going to come from the image plus 1, or the second image in the left camera, using SIFT, using our mask. And yeah, so now that we have key points and descriptors, we can get our matches. So we use our match features, and we pass in descriptors 0, descriptors 1, matching is BF, and the detector was indeed SIFT that we used. That'll tell it to use Euclidean distance, also known as L2. And let's just say sort equals false. I'm going to set sort equals false up here too, because I did this for some reason, and I can't remember what, and it'll probably come up at some point, but I just don't like it being on, because it's changing the order of my key points and descriptors. I don't like that. So, so let's just go ahead and visualize matches of image left, the key points for that image, and then image plus 1, and then the key points for that image, and then the matches that we found. And this should, what happened? Expected match for argument matches 1 to 2. Okay, you know what the problem is that these key points and descriptors are still bundled with their two nearest neighbors. So there's actually for each key point, oh, it's the matches, because these matches are a list of, let's check the shape of our matches here. What type is matches? We get some more space here so that we're not staring at the bottom of the screen. So matches, okay, it's a list. And then if we look at the type of the first element of matches, it's also a list. And so this is what's confusing the CV2 function, is that we have to give it a single match. And so let's just take a look at matches 0 actually, see what we got. No, they're just objects, so let's not worry too much about that. So what we need to do here is do a quick little list iteration and say that matches equals match first item for match in matches. And that's just going to get us down to a single dimension. Okay, let's see if this is going to work for us here. Earlier I was using a external PLT window, so I need to go ahead and fix that real quick, and we're going to pop back into matplotlib inline so that we can see what I'm doing. Okay, so this is a mess. There we can see that there are indeed matches being drawn between the two images, but there's a gazillion of them, and we can see that some of them are not very good at all. You know, good matches between a stereo pair of images. Well, this isn't actually a stereo pair, my bad. This is two sequential images, but we can see that there are things in the top right part of the first image that are being matched to things all the way down in the bottom left, bottom right of the second image. These are probably not good matches, you know, because things just don't move like that in 1/10 of a second, which is the frame rate of our camera. Excuse me. I have some water this time, forgot that in the last video. So yeah, this is a mess. This is not useful. So we're going to need to filter our matches. And so we're going to make a function called filter matches, and we're going to do exactly that. So we're going to say def filter matches distance, and we're going to take in a list of matches, and we're going to take in a distance threshold to filter them by. And so this is going to be a pretty simple function. We're just going to make an empty list called filtered match there, and then we're going to say for m n in matches, we're going to say if m dot distance. Okay. M and N here are the two matches because we had set it to two nearest neighbors. So matches is a list of two item lists that contain matches. And each of those matches is going to have a distance why do I keep a distance variable, you know, class variable attached to it that describes. As a matter of fact, let's take a closer look here. We'll take matches 0, which we affirmed earlier. Oh, I already did the list iteration. So let me just, I'm going to take this line here because we already went through and canceled all that stuff out. So let's remake our matches. And so now we see that matches is a list, and that each element of that list is a list of 2 matches because we told it to give us 2 matches for each key point or feature, you know. So let's take the first element, which is going to be a dmatch object here, and see what kind of things it has attached to it. So it has distance, it's got the query index and the train index. So this is going to be the index of the feature in the query image, which I believe is the, can't remember if that's the first or the second image in OpenCV. We'll find out in a minute. But basically, okay, so the query image, and then there's a train image. And I think that the train image is the second image that you're matching to. But either way, so obviously for each image, you're going to have a list of features. And so if you make a match between those features, the indices of the feature that you're matching between the 2 images isn't necessarily the same. So this is why you have attached to your match the index of the feature in each of the pictures. And so this is actually why the sorting doesn't matter now that I'm thinking about it, which is why I can probably set that back to true, is because it keeps track of the index of the feature that it has matched in the first and second image. And then the distance is going to be, of course, the Euclidean distance between the 2 descriptors, which doesn't really mean much to us other than the fact that it was chosen because of, you know, this distance was relatively close. But let's also consider that the second, so this is going to be the second closest match to this feature that we're talking about also has a distance. Okay, and these distances are pretty close. You know, there's not a lot of difference between them, and let me think of how to do this ratio. Let's just, anyways, the point is pretty clear at this point, is that the distance between the feature that has been the closest descriptor in the second image to the feature in the first image, and then the distance to the second closest descriptor distance to the same feature in the first image are pretty close together, which means that this is not a powerful feature because it hasn't really made up its mind which thing it really properly matches with. And this is exactly why we told it to give us 2 results per feature, because if the results, as we see, are close together, this feature is not well defined. It's giving us a fudgy kind of answer. So we want to filter this. And so as we can see here, we're taking an item from matches, which will be, say, this, and then we're going to take m and n from that match, which will be 0 and 1. And so if m dot distance is less than or equal to the distance threshold times n dot distance, then we will go ahead and append it to our filtered match. I really would like this to be called filtered matches. I feel like that's a better word, so it's not going to matter in the long run. And then we'll return our filtered matches. So the distance threshold, let me find out if OpenCV has a good documentation here for this ratio test. Sorry, I should have had this pulled up before I started the video, but it is important, I think. Okay, here we go. Yeah, so it was Lowe propose this ratio test. And usually they say, well, you can see here that there's a peak here around 0.5, which means that really, if you want to make sure that your feature is a good, solid feature that doesn't have other features in the next image that is like, well, we don't know exactly which one of these features is it's associated with. If you want to make sure you're like, this is definitely the same feature, then you probably want it to be at least twice as you want the distance between the first and the second match to be about double. And so clearly this first match that we found over here, it doesn't meet that criteria. So if we were to pick a distance threshold of 0.5, then basically we'd say, does matches 0, 0, is that less than or equal to matches 0, 1, distance, forgot that. It would, oh, it is less than, but we need to say 0.5 times that, and that'll be false because it isn't, and that's because if we were to try and figure out what the ratio between them is, try and figure out how this math would work to find the proper ratio. I think you just divide them by each other. Like I know how it works when you multiply by the ratio, but yeah, I think you just divide them by each other. Because yeah, okay, so this is the thing, is that this match is like 93% of the distance that this match is. And so this is exactly why we're doing this ratio filtering, because that's not an appreciable difference between these distances. They're mostly similar. And so we want things, because, you know, let's say that the first distance was, I don't know, say 150, right? And the second distance was 300. Then we get a ratio of 0.5, which would be our cutoff point. And so we're saying, you know, we don't want any features that doesn't have at least double the distance of the best matched feature in the second image versus the second best match in the second image. We want those distances to be at least twice as far apart. And that's going to determine what is or isn't a good match. So I'm going to set this equal to 0.5 as like a standard value, because as we, you know, we see this useful graph over here that, you know, they have kind of found that the correct matches tends to be the highest. It has a maximum point, looks like around 0.45, so we could set it to that. And then you can see this, the PDF for the incorrect matches, it goes up as we approach not filtering at all. And so as we saw before, we had a 93, you know, a 0.93 ratio between the two features. So that's a pretty probably not a correct match. So this is an essential step in doing photogrammetric visual odometry, is making sure that you're filtering your matches based on these nearest neighbor distance ratios. So I hope that that explanation has been thorough. And so now, instead of doing this cheesy line here where we're, you know, just doing that thing, we're going to let's give ourselves a print statement that says number of matches, and don't need to capitalize, matches before filtering, and say length of matches, and then we'll re-instantiate matches by passing filter matches distance matches, and we'll keep 0.5 for now, and print the number of matches after matches, and then we'll go ahead and draw the matches. Right, so things have cleaned up significantly here. We started off with near 3,000 matches. Now we're down to 917 just by using this 0.5 ratio threshold for making sure that these are good features. And we can see that this has effectively made the features that we're tracking better, because you can see how all these lines are very horizontal. We're talking about two pictures that were taken a tenth of a second apart. So as before, you don't expect the same thing in two pictures that were taken a tenth of a second as the car is moving at, you know, maybe 20, 25 miles an hour or 30 through this neighborhood here, to have moved drastically between one image and the other. You know, we're picking up parts of the corners of the license plate, these parts of the building over here, which are distinct, certain branches of these trees, some poles, parts of the sidewalk, and, you know, so we can take this a step further. What if we reduced this ratio threshold even further and said 0.3? How would that look? So we see we've cut our number in half again. We're down to 445 matches, which is still plenty of matches. I mean, the perspective endpoint algorithm only requires, like, you know, a few, and then we use ransack to figure out what the ransack stands for random sample consensus. And so basically you use an algorithm to use a few points to give yourself a an estimated rotation and translation. So essentially a transformation matrix between the position of the camera in the first frame, the position of the camera in the second frame. And then it uses that transformation matrix and applies it to all of the points, and it figures out how many of the points now seem to agree, what percentage of them, and what percentage of them seem to not agree with that that proposed transformation. And then once you have enough of your sample all in consensus to say, you know, okay, 90% of these points are matching given this estimated transformation that we have produced given the perspective endpoint algorithm's output, then you take all of the agreed points, all of the ones that were in consensus, and then you estimate another transformation matrix using those points, because now you've determined which points seem to all be in agreement with each other, and then you get an even better estimate using them to produce another estimate of your transformation matrix, because that's assuming if it wasn't, let's say 90% of them were in agreement, then the other 10% were like, maybe they were bad matches. They just, you know, wrong leaf on the tree or something like that. So you just sort of decide these are no good. Then we use these 90% and do the math again and come up with the transformation that satisfies these 90% of consensual points. So that's what we'll be doing. And so as you can see, reducing this ratio, it gets stricter and stricter on how distinct are these points really. And you can see that, you know, it's got like it picks some interesting stuff to like go through and see, like, this is a point in the grass over here, but apparently that is one hell of a blade of grass. You know, it's really distinct. And so this is going to work. So cool. We're at this point. I hope that I'm not going way over time here. Yeah, already over an hour. I sure do take my time. You know, I explain these things kind of in a lot of detail, and I know that maybe I repeat myself, but you know, the idea is that this is, you know, supposed to be sort of an intuitive tutorial series, you know, or I'm trying to explain things on like an intuitive level that, you know, is sort of like when you're watching a YouTube video and to have somebody explain something to you, you're already, you know, having a conversation, you know. So I think I'm gonna, since, you know, this seems like a good place to stop this video, I might just go ahead and start up a new video right after this, just to make sure that this doesn't become a 2 hour long thing, which it will if I keep this one going, because this is a clean place to stop. You know, we have taken our, well, you know, really all we've done in this video is feature matching. But there's a lot to talk about when it comes to feature matching, because, you know, one thing I can do before we go on the feature matching video here, as it has turned out to be, will be to let's run this process again, but let's use orb. So copy and paste this cell, and we'll tell it to do orb this time. Probably be better to have a single variable set instead of writing it in 3 times, but you know, it's all right. Okay, so we can see that we've gotten quite a different result here. That this distance threshold, first of all, the orb only gave us 500 matches to begin with. So, and we had it automatically set so that up here it knows that if it's an orb matcher, then we need to use Hamming distance instead of L2 distance. So we structured that right into this process. So it seems like orb gives us significantly less matches before filtering. So only 500. And then by the time we tell it to use a ratio of 0.3 as a filter on the distances for the 2 nearest neighbors, we're all the way down to 19, and that's just not enough. So if we were going to use orb, let's see what happens if we go for a 0.5 here. So 103, it's still not giving us as much juice as SIFT was, but it is faster. And so let's, for the sake of argument, we're tying up the video here, but let's import date time, and we'll say start equals date time. Well, we don't want to start it there. Let's start it down here before the extraction starts. So start equals date time dot now, and we will stop timing after, well, we don't want it to time the visualization, so we'll put end here equals date time dot now, and give ourselves a little print, maybe up here, print time to match and filter, and we'll say n minus start. Yep, okay, and run that. So that took, I think that's a half of a second. Okay, so let's copy that and paste it the way it is. So I'll go through and make all these orb again. Orb, orb, orb. Right, see, it's like a 1/6 of the time or something like that, right around. Yeah, so significantly faster, but not as performant, because it's just like not only not giving us the number of feature matches that, you know, to start with, but also they aren't obviously as good, because when we set the same distance threshold, it's throwing almost all of them away, which means that these features are just not as good. And like I said, this is just me. I'm not exactly a pro at this stuff, you know, so if there's something I should be doing to make orb more effective, and somebody watching this video is like, you know, I know, let me know, please, because I would like to use orb. It's a lot faster. I know that there have been papers released that I've looked at that use orb in their pipeline and get great results, and just don't know exactly what is the secret sauce to make orb work on that level. So yeah, please let me know if anybody knows, you know, what I'm doing wrong there, if anything. And so this is going to be the reason that in the next video we're going to be using the SIFT descriptors, and knowing that it's not going to be operating in real time. I mean, you know, real-time operation is a problem that, you know, the leading researchers are always tackling. So it's like we're not setting our expectations for ourselves up to that level. We're just trying to make this visual odometry pipeline work and learn about all these cool things, that all the components that make that. So yeah, I'm going to go ahead and call the video here. We did feature matching, we discussed SIFT, we discussed orb, we talked about filtering matches with the Lowe ratio test. I'm going to provide the resources that I talked about a second ago, which is his YouTube channel. Check it out, absolutely, just it's great. And then I'll put links to the SIFT stuff here because that's useful, and I'll also put a link to this so that you can find this chart when you want it. And yeah, so thanks for watching. I'll see you in the next video.